Is that what you said? I can hear that. Okay. All right, let me share my screen. Share entire screen, this one. And there's that. We should be good to go. All right. Hi, everyone. My name is PY. I am an engineer at Block, the company formerly known as Square. And so today we're going to try to spend a little bit of time to talk about Macrobenchmark. I'm going to be looking at my screen, but I also have another screen where I can sort of see people. So if you don't hear what I said, if I'm cutting out, please let me know. All right, so this the next 30 minutes, hopefully 30 minutes, are going to have no slides. So only code and, doing stuff live. Hopefully it's going to work, but we'll see. All right, so let's talk a bit about Macrobenchmark. Macrobenchmark is a library that was released by Google to help with benchmarking UI performance of Android apps. And we released that a couple of years back. It's pretty great. But today I want to talk a little bit deeper and talk about going beyond just the results that you get from running a Macrobenchmark. So this was just my Blue Sky profile that I was showing, just to kind of like, if you're on Blue Sky, come chat. I'm at p-y.wtf. That stands for Who's That Frenchie? All right, so Macrobenchmark. A good way to get introduced to Macrobenchmark is this code lab available on the Android developer.android.com, and it's Jetpack Compose Macrobenchmark. So the idea with that code lab is they have you run a Macrobenchmark on an app, a simple app, and then find a bunch of problems, fix those problems, and run the Macrobenchmarks again and show the improvement in terms of performance. So we're going to look at that. I'm going to go quickly over what that looks like. So hopefully you can see the code that I'm the code that I'm showing. I'm just going to check. Seeing I'm screen sharing. I just want to see. Yeah, it looks good. All right. So there's an Android app. This is the code from the code lab. I'm not going to spend too much. I simplified it a bit to make it easier to understand. If you haven't, the goal is if you've never seen a Macrobenchmark before, you're going to be catching up, getting up to speed. So Macrobenchmark is at the core an Android UI test. And so what you're seeing here is a very normal Android UI test that runs on device. One thing that is different from maybe what you're used to with UI tests, normal Android UI tests typically run in the same process as your application. Here, the UI test will run as a separate process, and it will command the other process. It will use something called UI Automator, though it doesn't have to, but its job is to really drive the other app from a separate process. So we have a normal UI test. It's just a test method. And then in there's this little rule. That's where we start seeing Macrobenchmark specific things, right? And what this is saying is, in this test, we're going to run this scenario, that's the measure block, a number of times. We're going to repeat that. That's what we're going to benchmark. So I'm just going to go quickly through the parameters. That's the package of the app that's being tested. This is the metric that we want to capture. The point of a benchmark is to measure something. And so there are different things we could measure. In this case, what they had decided to go with that code lab is the frames. How long does a frame take to render? So there is an app that's going to be scrolling. The benchmark is going to be scrolling. And the idea is measuring the duration of every frame as you scroll and trying to improve that. The compilation mode is, well, how to compile the app, more dynamic with like ahead of the JIT or full ahead of time compilation. Startup mode, starting cold versus warm, the number of iterations of the benchmark, and if there's any setup code. And then so measure block is where the actual code is going to run of running the app. And this is using UI Automator, and this is all code they wrote for the code lab. Basically, it's somewhat easy to understand, right? Press home, start an activity, wait until there's a list on the screen, and then do a drag and wait a bit and then do another drag. Drag being like a scroll where your finger stays on the screen. Pretty simple. So we're gonna run this. I'm gonna have, I think I have an emulator started here. I'm gonna run this benchmark, and hopefully you can see it's not starting yet. It's building and deploying, and then it will run. And so you can see that it's loading a bunch of pictures, scrolling once, scrolling twice, returning, and then showing results, which you can see here. Let me scroll a bit. I'm going to close that up. Right, so here, this is showing me the results of running that benchmark. And it's kind of interesting. It's showing, so hopefully you know, but if you don't, I can try to explain what is a frame. A frame is, so on Android, we either use views or compose, and that creates a hierarchy. And then at some point, we get to run through all that and draw on the screen. And when that happens, that's what we call a frame. It means we're going to draw everything on the display, essentially. I'm simplifying, but that's the idea. And so this is saying, well, this benchmark that we just ran had a bit somewhere between, 119. Well, sorry, it just had 119 frames. It's the same number everywhere, because there was a single iteration of the benchmark. And then seeing here are two metrics. And here are the P50, P90, and P95 for those metrics. So let's look into what those metrics mean, actually. So I didn't quite explain what's going on when you run Macrobenchmark. So you're running code, test code, in another process, and it is in telling the system, hey, you need to click here, you need to click there on the other app, and then capturing some information, right? But there's a third process involved as well. And that third process is called Perfetto. And Perfetto is something that ships on all Android devices now. And it's essentially a little process that can listen to a bunch of signals from the system and from the app. And so as we run the benchmark, Perfetto records everything that's happening, including frames, including whatever we want to tell it. And then it reports that information, and then the test process, the Macrobenchmark process, can query Perfetto, the Perfetto process, asking information and then get that information back. And that is how those metrics are compiled. So the good news with Android and Jetpack in general is everything is open source. So we can look at the code. So this is, let me show you how those frame timing metrics are computed. And so essentially, this runs after the benchmark is done running, and Perfetto has captured all the information. There's different types of metrics, and they have this method called getMeasurement. And what is a measurement? Measurement is just a list of data points and a name, essentially. And so a metric can return several measurements, several lists of data points with different names. And so here, the first thing that happens is getting all data. And when you look at what that is, it is actually a giant SQL query. So this is running a giant SQL query against Perfetto, and then it's getting that data out and messing with it, and then emitting back a list of measurements. All right, so now, as I mentioned, it's using Perfetto, and what happens is with every iteration, a Perfetto trace is captured. So we can actually look at that. Let's see. So in our build folder, there's going to be outputs, and then here we'll find, I'll just open that up, open in Finder. So there is a trace file, and if I go to ui.perfetto.dev, I can just drop that in. Now, wow, there's a lot here. Oh, I should have mentioned that I did run the benchmark on an emulator, and that is mostly because I wanted you to see what that looked like running the benchmark. But normally you shouldn't be running it on an emulator. You need to be running it on a real device with the right number of CPU, the right behavior. So never use emulators for benchmarks. this is just for the purpose of this talk. So with that being said, what are we looking at here? This is a trace of everything that happened during the benchmark. And we can see the app under test here. And you can see the main thread with some work happening. And the first two rows, which are kind of interesting, are frames. And you can see the expected timelines, meaning when frames were expected to start and end. And you can see the actual timeline, when frames actually started and ended. And so what, if you remember a little earlier, I mentioned that, let's see, here we looked at the screen, the results, and we saw that it shows frame duration CPU milliseconds and frame overrun milliseconds. Well, what are those things? The frame duration, the way it is computed, is it's from, let me pick a frame. So if I actually need to do that, if I pick this frame, so frame number 36300, the frame started here, right here, but it ended when the render thread, which is below, finished. So I can show you. So as you can see, let me show you here, it says 36300, and here it also says 36300. So there's work happening on the main thread, and then the work is passed on to the render thread. And when that ends, that's when that's the full duration of a frame. So here, that frame is about 17 milliseconds, and that's what the first metric we look at, CPU duration. CPU computes exactly this from the start here to the end here. Overrun is different. Overrun is we have an expected end, so we have the expected timeline, and every frame is expected to be done by this time. And sometimes they don't, they run later. And so overrun is, for example, if I look at this one, it was expected to finish here, but it finished here. And the overrun is this part, how long it went over. All right, so what's interesting about overrun is if you're late, you're going to have a positive value. But if you finish the work early, you're going to have a negative value. So it's kind of different in that way. All right, so we sort of had a quick, exploration of Perfetto. I gave some talks before around exploring Perfetto. I know it's a bit intimidating, but I promise you it's incredibly valuable to understand what's going on. Finally, one thing I should mention here is this P50. I don't know how familiar folks are with what a P50, a P90 is. We can see how it's computed because, again, everything's open source. And so there's this metric result class, which has a P50 that is computed here. So P50, P stands for percentile. And the way you can think about it, when you think about a P50, it is the value. So if you think about all of the values we capture, the frame durations, if we sort them from the lowest value to the highest value, the P50 is where 50% of the values are below it and 50% are above it. The P90 is the value where 90% of the values are below it and 10% are above it. So the way that you compute a percentile really is you sort the data. And this might look complex, but really it's just saying, well, you have that many entries in the array and we want to get at, say, 90%. So if we have 200 entries, it's going to be index 180, right? And just pick that value. It's doing a little bit more math because what it's doing is if you're not finding the exact index corresponding to a percentile, you just find the one before and the one after, and you do a linear interpolation of the value. That's what lerp stands for, linear interpolation. That's what this is doing here. That's being called here. I'm not going to get into all those details yet, but suffice to say, a percentile really represents a sort of a breakpoint in your data, and it's a value that represents the way that I like to think about it, a P50, which is also called the median, really is a way to represent the experience at most frames. Well, it sort of represents the experience that most have, or for frames, it's like most frames, at least 50% of frames are below that and 50% are above that. And then the P90 is like 90% of frames are below that, so it's a pretty high value. It represents the worst 10% in a way. All right, so we talked about this. We're going to go back to the code lab, and as they, I'm not going to go do the whole code lab, but one interesting thing about it is they get you to capture, run the benchmark, do a bunch of improvements, run the benchmark again, and then get results. And what I'm interested in is this part. So to run the benchmark once, and they get P50 value for, here it was for frame overrun milliseconds, P90, P95. Then they make a bunch of optimizations, run it again, get 11 milliseconds. And so, conclude, it seems right, that the improvement is 171% of the P50. That sounds cool. However, that's not really what you should be doing. Here's why. What if I was to run the before benchmark? What if I was to run it twice? Would I get the exact same P50? Probably not, because I would get slightly different frame times, right? If I was to run it a bunch of times, every time I would get a slightly different P50. So then my improvement might not be 171%. Maybe if I keep doing this before and this after benchmark, sometimes I'll get 160%. Sometimes I'll get 180%. So what do I do with that? Unclear, right? Like, how do I pick the right value? If I come and tell my boss, hey, we improved everything by 180%, and then my colleague says, well, no, I just ran it again, it was 150%. Who's right? How do we figure that out? So I want to talk about that today. That was a bit of a long intro for that, because I like to look at code, but we're going to look into that. But the first thing to do, we're looking at a P50, we're looking at aggregate metrics in a way. And what I like to do is go see the data. I think it's very important to be able to see the data. And so for that, we need the actual data that was used to compute this before and this after. Unfortunately, I couldn't replicate this exact benchmark. They used a device that is too old. They used a really old device that it would have really bad performance, but I don't have that. It's like a Pixel, I don't know, 4 or something crazy. So I couldn't reproduce. However, what was nice is in the setup part, they shared the traces. So we have all these files, and I realized, oh, hold on, I can. So one thing I could do is, if you remember, we have, I think somewhere in here, we're looking at this, and in here we have this SQL query. So one thing we could do is try to run the query ourselves, because one thing I did not show you is in Perfetto, here, when you're looking at this, you can actually write SQL directly in here. So I guess I did write it before. Here, this is just a query that we were seeing inside the code. We're going to run it here, and it's going to give us the results that were returned to the Macrobenchmark code, exact same results. However, that's not exactly the data that's being used. They're doing transformations. So I figured, I don't really want this. I want everything Macrobenchmark is doing. And this is taking me to this project that I made. It's on GitHub. You can play with it, or you can just do it for yourself. So what I did is I made a new Android app, and I shoved the 4 Perfetto trace files that we saw earlier. I put them all in here in assets directory. And then I wrote a test that just copies the files and starts running Perfetto on device. Perfetto can run on your laptop. However, there is no Kotlin API for talking to that. There's only a Python API, and I couldn't be bothered to write some Python. So, and also the Macrobenchmark extension code is in Kotlin, and I wanted to use that. So I was like, you know what? I'll just shove all the files on a device and run Perfetto there. And so you can see that it's exactly what I'm doing. I am creating a frame timing metric and then running queries against that. And so what's interesting here is that if I run this thing, it's running it on device, but the device is still running. There's no UI involved. So it should be pretty quick. All right, so it's running this thing. And what it's telling me is it's pulling out the values out of those files. So earlier we saw there are 4 files here. I took the before file, the step 0, and the final file, the step 3. Final is supposed to be the, step 3 is supposed to be the optimized one. And so I said, okay, just give me the frame durations before and the frame overruns, all of the values. And it's just a giant list of all the values. So I had that. I realized, okay, what can I do to render that? I need to see what that looks like, right? Well, I thought I could write some code to graph this, but then I was lazy and I didn't want to go do that. And we're living in 2025, right? So guess what I did? I asked ChatGPT to do it for me. So I'm going to show you what I did in a second. I just want to make sure that I'm caught up on what I wanted to talk about. Yeah. So let's see. Yeah. All right. So what did I do? Here's what I did. I told ChatGPT, hey, so I'm running an Android macro benchmark. I don't even know if I needed to say all that stuff, but I was like, okay, capture 2 values. And I want you, for each of those 2 things, the frame durations and the frame overruns, I want you to graph a frequency polygon. So I'll get to what that means in a second. I explained a little bit what I wanted it to use and comparing before and after, and also graphing the values over time. And then I didn't even bother with files or anything. I just pasted the entire list of values in here, and I just let it run. So what the heck is a frequency polygon? We'll get to see the results. But essentially, it's a representation of the distribution of your sample data. So it's like a histogram. The idea is you take all of your data points and you create buckets of a fixed size. So you could say if a data point is between 0 and 20, it goes in the first bucket. If it's between 20 and 40, it goes in the second bucket. And then you count how many points you have in each bucket, and you draw a histogram where the height is the number of points in each bucket. You do that as a percentage of total population, and that helps represent how the data distributes around the range of values. So this is like a histogram, but a frequency polygon more specifically is essentially a line instead of being. I think histograms are they're cool, but they're hard to visualize because it's a bunch of rectangles. And when you see a curve, it's a lot easier to sort of think about it. So here's what that looked like. So what's nice is in ChatGPT, there's this thing called this toggle always show detail. I like to have that on all the time because then it shares all the code that it's writing for me, and I can spot check like, all right, what is this? So this part, I'm like, I don't know how to do this, but it looks like it's probably right. No idea. But the frequency polygon and some of the other things, I'm like, okay, that makes sense. I can check that. I'm showing you this. I'm not saying do this all the time, but I think this is a good way to start. You could turn that into Kotlin or use Python and then check it in and reuse it over time. So this is what I got, this one. Let me start with this one. All right, you can zoom in. This is what I saw. So yellow is before, blue is after, and I saw a bunch of spikes. So that means there's a lot of the density here means the percentage of data, if you will. So it's like about 25% of data is in these sections, probably a bit more, but that gives you an idea. And then there's a long tail of no data, but a few data points here and there. What's interesting about that is it means most frames have about the same time, but a very few frames have a very long duration. And that's kind of interesting. And I didn't know what to do with that. I was like, why are some frames super slow? But then I did this. I drew the frame durations over time, and it immediately jumps at you that it's not randomly distributed. The first frame in both cases is very slow. Then there's a bunch of fast frames, then a somewhat slow frames. Then it's like kind of like normal frames. And with overrun, we see so overrun being the time whether we went over or under the target. We see a similar pattern. So what do we make of that? Well, I started looking at the code of the test, And no, sorry, I actually looked at the preferred trace first. And I realized when I did that, that we could see sort of that same pattern. Look here. So the actual timeline, that's the column that's kind of interesting. You can see here, very slow frame, 122 milliseconds. That's incredibly high. Here, 97 milliseconds, also incredibly high. And most others are like pretty quick in the middle. What's going on? Well, these frames corresponds to the first frame of the activity. The activity started and rendering the first frame of the activity. That can be pretty slow. And then this frame actually corresponds to when the images are loaded. If you remember the benchmark, it starts with a bunch of images that are not loaded, and they start downloading from the network, and then they load. Now, the thing is, the point of that benchmark was to benchmark scrolling, not starting an activity and loading a bunch of images. And in fact, if you look for touch events, which are in this deliver input event row, you can see that they all happen around this purple stuff, which is way after the super slow frames, right? So this part is when the benchmark is actually benchmarking stuff. And these are just frames that are like not really useful, right? And you can also see that in the code where if we look at where we were here, the scenario like does, press home, start an activity, wait until the activity is ready, and then start. And so this wait for the thing, this list of items only show up when once the images are loaded. And so this is really the part we wanted to measure. So if I was to rewrite this benchmark, I would move all of this to the setup block and only measure the dragging. But again, I can't rerun this benchmark because I don't have a really old pixel to get the data. So what I figured is what I could do is take all this data, but remove all the frames that were before the first touch event. And so it's what I did in here, where I'm just going to change something. I already wrote that code. Oh, yeah. So I switched from data to data after input. And if you look at how that's computed, it's computed here. So essentially what I do is find the time of the first touch event. And that gives me the timestamp of the first touch event. And then I find all the frames before, and I count how many frames happened before that first touch event. And then I use the Macrobenchmark metrics to get all the measurements, but then I say, all right, just drop anything that happened before, which is here. If you look at data after input, it's data, but drop the first n frames that were before the inputs. So if we run this, now that I've changed it, we get a different set of data points. Right. So we get frame durations and frame overruns. We don't see the 200, etc. values here. So same output. So then I pasted that into ChatGPT again. I was very lazy. I should have turned that into real code. But, I asked it to do this again. This time it doesn't have that as much of a long tail. And you can visually see how the impact of their optimizations here, because you can see that so yellow is before, right? You can see that before and after have generally the same kind of shape, but the after is shifted to the left, meaning it's faster, right? Closer to zero. It's also really interesting to notice that there are two peaks and actually maybe three peaks. Most of the frames are in this super fast range on the left. A good number of frames are in the kind of slower, around 7.5 millisecond range, and then a couple of frames are around 12 milliseconds. When you see a distribution, and that's what I love about doing this sort of graphs, these distributions, it doesn't happen randomly. Like the fact that the distribution will go down and then back up doesn't mean, I don't know, random noise. It typically maps to real stuff. For example, when you look at the frames here, some frames, when you think about scrolling, what is it? Most of the time scrolling is just, you have a bunch of things, you're just moving a couple of pixels up, you've already rendered everything, and you're just shifting and translating. But sometimes you need to bring in a new item, and that could be, maybe it's that one. It's like, it's a bit slower because now we need to render an extra item, and then we're back to fast, 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 and then, oh, new item, we're slow again. So I think that's what those different sort of like peaks correspond to, is like the fast frames. Most of the frames are fast, some are slower. That's when we're bringing new items in. So here, the pattern over time is a lot less obvious. There's lots less correlation between the different values than it was maybe here, where we could see everything was sort of in sync. This one is sort of interesting. This is the same distribution, but for overruns, and you can see that. So this is negative values, right? Like it's most of the time we don't actually run out of time to render frames. Now that we've eliminated the really bad slow frames of the beginning. But in the before optimization, most of the frames were finishing between 3 and 4 milliseconds before the deadline. And it looks like now there's a very different shape of distribution, almost like a power law. I don't know, but it's like really condensed around, starting at minus 12 milliseconds, which is incredibly fast because we get 16 milliseconds per frame. So it's like only 4 milliseconds to do the work, and then it's sort of shifting down. So you know that the bulk of the frames are in here. All right, so that hopefully hopefully you knew everything about distributions and how to use that. But what I wanted to do, but if you didn't, I wanted to show you how it's really interesting to graph these things. So the keyword for ChatGPT is frequency polygon. For all the bullshit that ChatGPT will throw at you, it's been pretty good at this for me. As long as you keep asking, why are you telling me this? Show me the proof. Link to the article that demonstrates this or whatever. And then you keep digging and you get this. But as you can see, the prompts were not crazy, nothing smart. Now, back to, here, compare results. Like I think it's nice when you show this, or when you show this, it's visually everybody understands, oh, the blue shifted left, more left is more better, right? But it's hard to communicate that in a couple words or just as a number. So so it's nicer if you can say, well, the improvement was 171%. But as we saw, we don't know the exact percentage. So I'm going to bring in a little bit of stats without going too crazy. There's this idea called confidence intervals. And the idea is, well, I'm pretty sure that the improvement is between this percentage and that percentage. So how do we do that? There's a bunch of ways. One of the ways you can do that, I'll start with the prompt. So same thing, I'm pasting all the values. But one of the ways that I'm doing this is I'm telling ChatGPT, okay, I want to compute my median, my P50, with a 95% confidence interval. I'll tell you what that means in a bit. Using bootstrapping, and we'll talk about that. And I tell it what to do. So what is bootstrapping? The idea is, well, we talked about how if I run the two benchmarks again, I'm going to get a slightly different result, right? So we're going to fake run the benchmarks an infinite number of times. Not quite infinite, but a large number of times. How do we fake run the benchmarks? Well, we take our data set and we say, you know what? I'm going to pull out a bunch of values from that data set randomly. And I'm going to say, that's a new benchmark I just did. And then I'm going to do that again and do that again. And I'm just going to generate 100 or more fake benchmark from that initial data set. Every time I pull a value, I don't remove it from the original. So I could pull the same value twice, for example, in a single fake run. And I do that for the other one. And so now it's as if I had 100 different benchmarks to compare. And then we can compute something called a confidence interval, which, you know, it's actually done somewhere in here, bootstrap diff CI. So no, this Python method is what generates, what's pull data out of the arrays a large number of times randomly. Why is it okay to do that? I'm not a stats expert, but it's supposed to be okay. Anyway, it helps communicate things. And so then we get to, all right, how is that computed? And that's just Python doing its thing. But we get these results. And I'll share this. Maybe I'm just zoom out. Right. So this is what we get. Oh, no, I lost it. Oh, I'm back. Okay, cool. This is what we get. We say, all right, so for frame durations, which is a little bit easier to think about, the P50 was at 6 milliseconds. So the median was 6 milliseconds. And after the change is 4.5. So, and remember, this is the data set where we removed the very slow frames. So it's not the same results as what they were showing in the code lab. So we said, well, the P50 improved by 1.4 milliseconds. That's a 24% reduction. Now we get a confident interval. And so we say, well, okay, it's not 24, but it's, you know, it's not 1.4 milliseconds. It's probably somewhere between -2 and -1. I'm rounding up. And so that's good. So what does 95% interval mean? It means that if we kept running those benchmarks a large number of times, 95% of the time, the difference in the P50 would be between these two values. So we think that's good enough, you know. And so you can do the same with frame overruns, but because they're negative values, the interval is positive. So what's interesting about that is it communicates the certainty/uncertainty that you have about your data. And you'll find that, because if you say, well, I improved by 30%, that's one thing. But if you said, I think I improved between 10% and 70%, that's a lot of range. But it shows how certain or not you are. Now, the thing with bootstrapping, the technique we did, we sort of made up a bunch of data points. And so that's why the interval is fairly large. And if you wanted to shrink the interval, you could do these things for real and just run the benchmarks a large number of times, which in the benchmark code is really just changing this value to like 10 or 100 and just let it run. And then that would give you many more data points and probably a much more confident, like a smaller confidence interval. And with that, that's it. I went a bit over what I had planned to do, but yeah, that's me. I don't know if we have time for questions or next speaker. Let me know what we're doing.
Wow, I just want to jump in and say thank you so much, PY, for accepting to talk first and then also demonstrating that, because that was super cool. It's a topic I'm interested in and I love statistics. And actually, I was doing that in my previous class.
Nice.
So Naveed, back to you.
Yeah, thanks a lot for the talk. Sorry, we had some technical difficulties, so we were actually connected through a laptop. But I promise we have people here.
All right. Let me know if there are any questions. If not, we can move on. That's okay too.
Oh yeah, awesome. Are there any questions on Zoom?
I had a question,
Yes.
but I want to ask also New York is if they have a question. But I was just wondering, I think one thing that was pretty interesting for me was how you showed the P50, because I've never known how to read that value. But I'm wondering, do you think it calculates any junky frames, or how are the junky frames? How do we know if the junky frames are not even accounted for?
So if you think about jank, well, it depends what you're looking at, right?
Okay.
What we call jank is the frames that go over the budget. And so in this case, here we have jank. And here we have jank, and here we have jank. Jank means like, it sort of like didn't scroll neatly. It sort of froze the UI. And so it really just means you went over the 16 milliseconds budget for your frame. So there's a couple of things there. One thing you could do if you're looking for jank is just looking for count the number of frames or the percentage of frames that have frame overrun being greater than 0. Because frame overrun means, we ran over, we had jank. But the other thing you can do, if you just look at the actual frame duration like we were doing, by nature, jank is going to be, the janky frames are going to be the frames with the longer durations. So they're going to be the highest values in terms of frame duration. So if you think at the, when we talk about percentiles, we said we're sorting all the values, right? And the smaller on the left, the larger on the right. So the janky frames are going to be on the right. So if you say track the P50, the P90, sorry, the P90, or the P95 or the P99, this will give you the 10% worst, the value that is the separating between the 90% best and the 10% worst, or 95% best and 5% worst. So if you look at a P90, P95, or P99, that's where you will find the values for like the janky frames.
Thank you so much. Wow, pretty cool.
Awesome. Yeah, thanks for the talk. We do not have any more questions here. If New York has any questions, please feel free to ask. Otherwise, I think we're good here.
Cool. Well, thanks everybody. You should come to Blue Sky and stop using Twitter if you are. If you're not using any of those, that's okay. It's better for you anyway.
Cool. We are already in Blue Sky. Okay, thank you again so much, Pua. We do appreciate your time. And
all right.
We're going to let you go to sleep now.
Yeah, I'm going to go to bed. It's midnight. It's past midnight here. So, all right. Good night, everybody.
Thank you. Bye.